Welcome to This Explainer. Today, we're unpacking the hidden engineering complexities behind real-time AI voice support agents, specifically diving into Chapter 9 of our source material. If you've ever interacted with a voice AI that felt surprisingly natural, or maybe one that rudely talked right over you and left you incredibly frustrated, well, you've experienced the direct result of the system design choices we're going to explore today. To start us off, we really have to ask ourselves, why is transitioning from a basic text chatbot to a fluent voice agent such a massive leap in system design? It's a fascinating challenge. You see, in traditional text chat, if a system takes a few seconds to fetch information, it simply pops up a typing indicator, and the user waits patiently. But voice? Voice completely strips away that visual safety net? It all boils down to one critical constraint: the latency budget. This is the strict, sub-second window you have to process audio, think, and reply before the human caller actually perceives a dropped call. The discipline of building these systems hasn't fundamentally changed from standard machine learning design, but every single component must now be heavily optimized to fight this relentless race against the clock. Here is our agenda for this explainer, which is basically our blueprint for dissecting this architecture layer by layer. We'll cover the 1-second challenge, pipeline versus speech-to-speech architectures, the anatomy of a voice turn, handling interruptions, evaluating the system, and finally, scaling up under pressure. Let's get right into it. Section 1. The 1-second challenge, or as I like to call it, the anatomy of a millisecond. Let's explore this relentless race against the clock. Think about how incredibly fast human conversation actually is. When we talk to each other, the natural gap between turns sits at around 200 to 300 milliseconds. If you leave dead air on a phone line past roughly a second, well, it doesn't just feel slow. To the human ear, it literally reads as a dropped call. We've all had that sudden panic of, "Hello, are you still there?" This completely dictates that our most critical metric is time to first audio. The caller absolutely must hear the agent's reply begin within a fraction of a second. Moving right along to Section 2, pipeline versus speech-to-speech. This is the core architectural choice and the biggest crossroads in voice AI right now. When you're building the brain of the agent, you face a huge trade-off: pipeline versus speech-to-speech. The pipeline approach relies on 3 distinct stages: a streaming speech-to-text transcriber, an intermediate text-based language model, and a streaming text-to-speech synthesizer. Its biggest strength is observability. You can inspect every single text artifact in the middle to apply strict guardrails. On the flip side, a speech-to-speech model takes audio directly in and spits audio directly out. It's insanely fast and natively handles tone and pacing, but you trade away those clean, inspectable text seams. In the real world, prioritizing those inspectable seams over sheer speed is often the winning ticket. Take Intercom, for example. When they built their FinVoice agent, they intentionally chose the classic pipeline. Why? Because resolving customer issues involves high-stakes actions, like issuing refunds or altering billing info. They absolutely needed the control to inject conversational fillers, like, "Let me look into this for you," for queries taking 3 to 4 seconds, just to keep the line alive. And it worked. This choice allowed them to successfully resolve over half of all their customer conversations. Okay, Section 3, anatomy of a voice turn. Let's trace the exact life cycle of a single turn and build this pipeline step by step. Everything kicks off the exact moment the caller starts speaking. This requires an immediate, continuous audio stream piped directly into the system. You can't just wait for a file to upload. The data has to flow in real time the instant the words leave the caller's mouth. This activates voice activity detection, or VAD, which simply listens for speech versus silence. And that feeds right into our next stage, where streaming automatic speech recognition, or ASR, emits partial transcripts. This is honestly so clever. The system doesn't sit around waiting for the caller to finish their sentence. By streaming preliminary transcripts that are marked as not final, the brain of the agent can actually start retrieving data or routing the intent before the human has even stopped speaking. Finally, we complete the hop with streaming text-to-speech. As soon as the language model generates the very first few words of its reply, the TTS fires those first audio chunks straight back to the caller. This hits that critical time to first audio metric. Literally, by the time the AI is figuring out the end of its sentence, the caller is already hearing the beginning of it. But wait a second. How does the agent actually know you're done talking? Well, that brings us to endpointing. It's one of the highest leverage tuning knobs in the entire system. If you get this wrong, your agent is just going to constantly interrupt people mid-thought. Upgrading from a Dove silence timer to a smart semantic model is a total game changer. A basic silence timer just waits for a set gap of quiet, but humans pause to think. Semantic turn detection, on the other hand, actually reads the linguistic context. Take LiveKit's open weight 135 million parameter model. It runs on a CPU and knows that if you say, "My order number is," and then pause, you still hold the floor. But if you ask, "Where's my order?" it releases the floor immediately. It saves precious milliseconds without rudely cutting you off.
Section 4. Handling interruptions and barge in. Humans are messy, right? We constantly interrupt, trail off, or change our minds mid-sentence.
The second a human interrupts to correct an order or just cut an answer short, the system has to react instantly. This is an absolute necessity for making a call feel natural. If a system forces you to sit there and listen to a 30-second monologue without letting you interject, it just feels like a broken robot. To pull this off elegantly, the system follows 4 very specific steps. First, it needs duplex audio, meaning it has to actively listen while it's speaking. Second, voice activity detection registers the caller's voice. Third, it immediately ducks or stops its own text-to-speech audio. And fourth, it clears out its half-formed reply and replans based on the new input. Now, a major subtlety here is making sure the system doesn't confuse a back channel, like you just saying "aha" to show you're listening, with a full interruption. If it gets that wrong, the agent will just flinch and stop constantly. Section 5. Evaluating the voice agent. Building the thing is only half the battle. Let's pivot and see how we guarantee this agent actually sounds natural and works correctly. Because phone audio is inherently noisy, we have to map specific voice failure modes to exact quantifiable metrics. If the speech recognition mishears names or order numbers, we measure that using word error rate. If the audio output sounds robotic or mispronounces domain terms, we measure that via a human-sampled mean opinion score. And for turn-taking, if the agent cuts the caller off, we track the false barge-in rate. You literally have to score each component against a reference dataset of real audio to make absolutely sure it's safe for production. Section 6. Scaling up under pressure. For our final structural section, let's talk about what happens when 10,000 people call your AI agent at the exact same time. It turns out, scaling voice is vastly different from scaling chat. Unlike a standard web server handling quick stateless pings, you have to scale concurrent, stateful sessions. Every single active call holds an open speech-to-text stream, a text-to-speech stream, and a model session for the entire duration of the call. The compute bottleneck isn't just the text model anymore, it's the continuous speech services running per call. And critically, you absolutely cannot put a live speaking caller into a loading queue while they wait for a server to spin up. To keep that latency budget intact under heavy load, engineers use a specific arsenal of optimization tactics. They aggressively pool and auto-scale the speech services for peak concurrency. They route routine, repeated questions to smaller, faster models and use semantic caching. They also deploy session-aware load balancing. This ensures that, even during a massive traffic spike, the system degrades gracefully, maybe by playing a brief hold message rather than just dropping calls mid-sentence. As a quick glimpse into the feature, the experimental Moshi speech-to-speech model from Qtai is currently pushing the absolute theoretical ceiling of latency down to just 160 milliseconds. It models the caller's stream and its own stream in parallel. This means explicit speaker turns disappear entirely, and overlapping speech is handled natively. That is the staggering performance ceiling this entire architecture is actively chasing today. As we wrap up this explainer, I'll leave you with this provocative thought. Mastering voice AI isn't really about the talking. It is entirely about engineering the art of listening. From streaming partial transcripts to semantic endpointing to duplex barge-in handling, every major hurdle in voice system design comes down to understanding exactly what the human is doing at any given millisecond. Thank you for joining me, and I hope this gave you a clear window into the incredible engineering behind the next generation of voice agents.